into two major domains. One is your digital domain, and the other one is your analog domain. So the moment you are talking about analog domain, you are talking of transistor which are not of very high order. By what do you mean by very high order is that the number of transistor, the number of transistor that you may use to make a say operational amplifier or a differential amplifier or things like that would not require you a huge number of transistors. So this is again a very basic uh, thing that you need to know, which will be further expanded as you will be doing courses on your analog IC design. Remember, the transistor uh, is more or less the same, but which is generally the MOSFET transistor, whether you talk of digital or whether you talk of analog. But the type of transistor, the type, the domain in which the transistor is being used, and the number of transistors are very different in analog and very different in digital. So we will. So as I mentioned, the number of transistors are low. That is why the whole of analog IC design is not called a VLSI design. So what do you mean by VLSI design? Because this course is on introduction, you should be knowing. Uh, VLSI is like the expanded form is, anybody? What is VLSI? Anybody?
So very large scale integrated systems.
Okay, what does that mean? Good, 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 good. That's a, yeah. What does that mean?
So basically, there's more components embedded onto a chip.
Now this doesn't make sense. What does what does that mean? Yeah, anybody? Yes,
And
anybody?
both of them are
Uh, Hello. Please tell me. Yes, anybody? Okay. Anybody has any idea? Okay. So we have talked about the analog IC design. The operation of the transistor is different from the digital IC. The number of transistor in analog is far, far less than your analog IC design, and also in terms of its operation and other parameters, it's very different. I mean, the type of transistor, I mean, like there may be a difference in the technology node itself between the analog IC design and the digital IC design. So an analog IC design, the transistor size may be far much bigger than your digital IC design, because anybody has anything to elaborate on that? Hello, hello.
Yes, sir, you're audible.
Yeah, no, I'm asking you a question. I'm asking you a question. Can you throw some light on that?
So, so in analog devices, our main goal is to create
devices which will be used for gaining for more uh, power. No, sir, so I'm not sure exactly.
Okay, so the important point that I want to make is, since the number of transistors to make an analog circuit, like an amplifier, differential amplifier, operational amplifier, so on and so forth, the the idea is to have better bandwidth, better gain, better common mode rejection ratio, better PSRR. These are things you may have done or may not have done, but at least you must be knowing about gain and bandwidth and noise and stuff like that. So the number of transistor, sheer number of transistor that is required is not large enough. Okay, so that means that even if you are using a, 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 a old dated technology, you can still get very good results. Okay, now having this as a knowledge, now let's change over to digital. Digital, the first thing that comes to your mind is like the microprocessor. That's how the whole VLSI or the IT industry came into being, or the Silicon Valley came into being. Okay, so the moment you are starting to talk about microprocessor, which you also studied in your last semester, you are constantly talking about increasing the number of transistors. That is governed by the very famous Moore's law. What did Moore's law state? Moore's law stated that the number of transistor after every 18 or 24 months is almost getting doubled per unit chip area. So that has been the guiding principle for digital IC design, that you're constantly pushing to have more and more number of transistor in the same area. Analog doesn't require that. Analog only requires, why it doesn't require that? Because it can make, you can make an amplifier with very little number of transistors. So technology, or even in terms of number of transistor, is is not is not required for making an analog IC design. Though there should not be a very big difference in the technology node, whether you're talking about analog or digital. Okay, so what has been happening? Initially, all it started was when we were using these for in the 1960s. We had the number of transistors which was of the order of, anybody? Anybody?
So can you please repeat the question?
Initially, the number of transistors that came in your, say, 4004 microprocessor, how many transistors were there? Moment you're talking about microprocessor or memories or all kind of combinational or sequential circuits, you're talking about digital design. So to make a microprocessor, the first microprocessor, which was the first microprocessor? It was Intel. Hello? It was Intel
Sir, 404.
4004.
4.
So what was its technology nodes and how many number of transistors?
Sir, some 100 million, some transistors.
100 million? No, 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 no. Okay, can you see the website here? I think we go straight to the Intel website. Can you see the website, please?
So you're not presenting the screen.
Oh, why? So you should at least tell me ki, something is missing, something is not missing.
Sir, no, but whatever you were saying up until now was not really related to something on the screen anyway.
But I talked about I talked about VLSI per se, and now I'm talking about what's there in the screen. Can you see this? Is this visible?
Sir, it's a black screen.
Sorry, just a moment. Can you see this?
Yes, sir.
Right. So the first microprocessor, 1971. Okay, and that was what was the processor name? 4004. So there was no millions and millions of transistors. How many transistors were there? Anybody? It was very big because the dimension of the transistor itself was huge. It was, what was the technology node in terms of transistor, in terms of the gate length or the channel length? It was 10 micrometer. Okay, so how many number of transistors they were using? Intel, we're just going to be talking about Intel. How many transistors they were using? Can you read this? 4004, can you please read
Yes,
this?
sir, 2300.
2300 only. 2300 only. And as time has progressed, the number of transistors have gone towards billion. It is 0.56 million transistors. This is for 32. The technology is below 32 already. So this was the initial transistor. So this is how we have defined. I mean, like, it started with what you call as, so can I just, so you can actually have a look at all these things. What happened at the very initial stage? What was the technology node? Technology node, we will just, then what is the famous Moore's law? Then Robert Noyce's law. Okay, so it all started with them. Can you see this slide? Am I visible or not?
Sir, it
Yes,
is
sir.
visible.
Sir, you stopped sharing your screen. It was visible.
Okay, okay. I just do that again. Just do that. Can you see this?
Sir,
Sir,
you're
you're
not
not.
sharing your screen.
Can you see now?
So you're not presenting.
I grew up in small town America, which had to be self-sufficient. If something was broke, you fix it
Yeah,
yourself.
can you see this?
I was.
Can you see this?
Yes, sir. Yes, sir.
Yeah. So as we said, as we have seen in 400, you had few hundreds of transistors. So those circuits which had that small number of transistors, remember, whenever we are talking about VLSI or other domains, we are actually talking about digital IC design. And as time has progressed, it's only in digital IC design that the number of transistors that are involved to make the circuits or make processor or make memory or make any of the uh, different types of digital modules, whether it's a combinational circuit based or a sequential circuit based, the number of transistors have kind of increased. While in analog, you never needed any higher number of transistors. Okay, so we are not talking about huge numbers in analog. We're just talking about very few hundreds to thousands of transistors. That's all. But for digital electronics, there was a miniaturization of these transistors because you needed to have more and more number of transistor per unit volume. So we will be also talking about what happened, how did this miniaturization happen. But to begin with, the basic thing is that as time progressed, according to the governing principle of Moore's law, which stated that every 18 to 24 months the number of transistor keeps on getting doubled. So that is how the whole Silicon Valley and this thing has happened, and it's going on, and I think till eternity it will happen. It will happen based on these transistors. So when you had the number of transistors ranging from 1 to 100, and the circuits that was made, circuit basically means the digital circuits. They can be combinational based or sequential based. Okay, so these digital circuits were named as your SSI, small scale integrated circuits. Then when it went per unit area from 10 to power 2 to 10 to power 3, which is like up to 1000, the circuits that was made of them, that was called the MSI, the medium scale integrated circuits. Then when it went from 10 power 3 to 10 power 5, then they were called the LSI circuits. So like in the 80s and all, 80s and then early 90s, there was a
Excuse me, sir.
so they were called large scale integrated circuits. Then
Excuse me.
came the era of 10 power 5 to 10 power 7, which is hovering around the million. So they were called the VLSI. And since then, you are having these different types of IEEE sections which is having VLSI. So beyond 10 million transistors is getting into the billion domain, right? Even with just now you may have seen the 32 nanometer, they were talking about hundreds, thousands, hundreds and thousands of your 100 million or 1,000 million transistor, which was going towards the ULSI domain, which was ultra large scale indicator, so billion to trillion number of transistors. So that is what we are talking about. Yeah, go ahead. There was somebody who was asking me a question. Yeah.
Sir, were you presenting something because only the Google Meet uh, the slide is like the tab is visible?
Oh, you didn't see this?
No.
Mm-hmm. How's that? Let me do that once again. Can you see now? Can you see now?
Yes, sir. Now
Yes,
it's
sir.
visible.
Yeah, please note down these things. These are very important. SSI, MSI, LSI, VLSI, and ULSI. So moment we are talking about digital IC design, we are talking in terms of the, the building block happens to be transistor. And as time is progressing from 70s to 80s, 80s to 90s, 90s to 2000 millennium, and beyond that, there's a constant demand and requirement of industry to keep doubling your transistor. Why keep doubling? Because number of transistors you want is to increase. That means more and more circuits, that means more and more modules per unit chip area. The important thing is the area doesn't change, but number of transistors keeps on doubling every 18 to 24 months. So what happens once you have that 18 to 24 months? You are what probably you were able to do in 70s. They were taking huge space. Now they hardly take any space. That is why all your old computers, laptop, desktop, palm tops, smart or your mobile phones, they were all so bulky in nature. It's because of this digital. Initially everything happened in analog, even communication happened in analog. Now everything is digital. It's all happening in zeros and one. Everything is in digital. So you need to do digital IC design of the combinational circuits or the sequential circuits or the extended mode of the digital, which requires or which basically demands that the area or the volume that is occupied by one module is constantly miniaturized. And this basically states that how different eras have evolved over a period of time. So it started in the 1970s, then 80s, then 90s, then 2000 and beyond, and presently in 2010 and beyond. So now we are talking from billion to trillion number of transistors, 10 power 9 to 10 power 12 number of transistors. As you can actually see, that definitely is depending on the technology node, which is basically talking about the geometry, which is basically talking about the area or the volume a single transistor occupies. So if you if your transistor size is going smaller and smaller, you can have density going higher and higher. So this is exclusively for digital IC design. This is the starting point, and it all boils down to your transistor. So you would come across SSI, MSI, LSI, but then VLSI onwards. So some people they did not change. You have a lot of these IEEE based journals and conferences. They all call it semiconductor, VLSI, or IT. So they're all talking about this thing. So they have not updated it. It is already changed to the ULSI part of it. But it's very traditional. It's all understood. Is that clear? Hello?
Yes, sir.
So now since we say, okay, what is the basic? What is the building block? It happens to be transistor. So now we need to study the operation of transistor. Again, we will not talk about analog. Analog, the operation of transistor is very the part which is used for analog operation of the transistor is very different from that of your digital. So in analog, that part is used which is basically for your amplification, while for digital it is used as a simple switch. Can you see the slide? Can you see
Yes,
this?
sir.
Huh?
Yes, sir. Yes, sir.
Okay. So I think again so in the beginning itself, it was all boiling down to MOSFET. It was all boiling down to the BGT. So initially, the transistor invention happened. It happened way back in around when we got our independence, and then people have got Nobel Prize for it. It was shared between three physicists, and from there, this whole Silicon Valley actually arrived. Okay, but the BGT is not the present form, basically because it has, again, when we are saying we are actually concentrating on the digital IC design, because most of the time we are talking about microprocessors or memories or other types of digital circuits and stuff like that. So in that it's not good because it was very leaky in nature. And the other important thing why the BGT could not make it, again, I will not go into details, I will just give you very salient points why BGT could not compete with the MOSFET type of transistor. There were two major reasons. First, it was very leaky. So there was a lot of leakage current that was happening. So it was very bad. Second, the miniaturization, the squeezing of the transistor, miniaturization of the transistor, going from 10 power 3 to 10 power 6 per unit area was almost impossible in the BGT type of transistor configuration. While MOSFET transistor, these two major drawbacks of the BGT, specifically for digital application, the MOSFET type of transistor was able to overcome the two major challenges that was posed by the BGT transistor. So now we go in specific about MOSFET transistor. Remember, nowadays when we talk of transistor, most of the times it is MOSFET transistor, whether we talk of analog IC design or digital IC design. Though we just said that analog may be BGT may be good for digital, but still we are using MOSFET. And we will, I mean, like if you do courses on the analog IC design, you will know why. So now we come back to the digital IC design. So whenever we are talking about digital IC design, as the number of transistors is going on increasing, we are defining different eras in which we will be talking off lately about the VLSI era or the ULSI. It's all the same. So we are talking about million to billion and beyond. number of transistors that are involved in making a circuit per unit area. So in this digital design, the MOSFET is used as a switch. The MOSFET is used as a switch. So we shall just, you can see from this slide, we will just be talking about the salient features of the MOSFET transistor. I think we had already started. Forget BJT, forget analog IC design, forget analog electronics for this course. Now we just concentrate on MOSFET structure and then build up to your CMOS technology. And then we talk about the types of MOSFET. So the MOSFET structure, the types of MOSFET, okay. Then we talk about the threshold voltage of MOSFET. That is why you need to know the MOSFET transistor inside out. So device. So MOSFET is basically made of different types of junctions. PN junction, N plus P junction, P plus N junction, metal semiconductor junction, metal oxide semiconductor junctions, so on and so forth. So MOSFET is sum total of all different types of junction, and that probably you may have done a course in your previous, and that is why you are having all those depletion region and what you call as the inversion region. So after this, we will be talking about a novel concept again, which is responsible for the flow of current, and that is, I think it's one of the most important concept in the MOSFET transistor technology. So what is the full form of MOSFET? Anybody? What is the full form of MOSFET?
Some metal oxide semiconductor field effect transistor.
Okay, why do we call, okay, so metal oxide semiconductor field effect transistor. Okay, so the most important characteristics or parameter which basically drives the MOSFET transistor is the threshold voltage. After this, we will be talking about the current voltage, ID, VD, current voltage characteristics, and the transfer characteristics, which is drain ID, VG, drain current versus gate voltage. So because there are two types of field, again we will first show you the basic equation and the whole thing. So because we are talking about yeah, can you see this slide? Hello?
Yes, sir.
Okay. So we've already talked about metal oxide semiconductor field effect transistor. Why is it called field? Because you are having the current being going from, say in this case, this is the N type of transistor going from source to drain. So actually a MOS device is a 4-terminal device. Terminal means it has, you need to have biases, or you can use the bias in all these 4 different types of terminal. One is the drain terminal, second one is the gate terminal, third one is the source terminal, and then the body terminal. So in all these terminals you can give certain bias. Okay, so MOSFET, now we're just going to concentrate on MOSFET transistor. MOSFET is a 4-terminal device, okay, and can be considered as a switch. The moment we are talking about digital, we are talking of transistor operation either in 0 state or in state 1. We are not talking as an amplifier. That is the domain of analog IC design. And that can be achieved by achieving proper biasing among the four terminals, that is gate, source, drain, and the bottom body. Okay, so these basically, the voltage that you have it here, the concentration, the doping concentration at source, drain, and in between the PN junctions which is formed here, that will define the depletion width. Anyways, what is depletion width? Anybody? What is depletion width? Again, that's a concept that you should relate to your previous knowledge on MOSFET transistor device. What is depletion width? Navratan, you there? Sai Sudhir?
Yes, sir.
Huh. Bolo, what is depletion width? We did talk about PN junction. So PN junction, if
Due to
you, let me
the
just complete my statement and then,
so there would be a depletion region so that current can pass from there.
huh? Now, when I was saying, you were also saying something. So you go ahead, complete your statement. Navratan, go ahead.
Yeah, yes, sir.
Huh. Be louder and so that we can all hear you. Manas? Ishan? Sanya? Am I audible or no?
So you're audible.
Okay.
So between the PN junction, because of the because of the density difference of electrons and holes, uh, there's between the junction, the junction region, a region has created where density of carrier charges decreases. That is called as depletion region.
So if you take, again, I'm just trying to summarize those who have not done this before, they need to do it by themselves, and those who have done this before just need to revise your previous knowledge. For simplification, I'm just trying to revise and repeating few things, which is very essential because it becomes the building block for any transistor and any circuits that we talk about. So what is that? That is the PN junction. So basically, whenever you're talking about a simple PN junction, that is, you're having P where your holes are a majority carrier. Whenever we are talking about majority carrier, we are talking more than far greater than the intrinsic value. Remember, the baseline for all the semiconductor that we are choosing is silicon, and silicon happens to be having intrinsic value of around 10 power 10. So we are talking about 10 power 15 to 10 power 18. So 14 to, then it becomes n or n plus plus or p and p plus plus. So when we are, and then whenever we talk about, it also has minority carriers. So minority carriers, when we are talking about 10 power 5, 10 power 6, 7, 8, something like that. So the moment you get a p type of material and n type, so n would have electrons as a majority carriers, and P will have holes as a majority carriers, and will have holes as a minority carrier, while P would have electrons as a minority carrier. Now, when they are going back to back or switched to each other, what happens is there are two important concepts that is happening. One is the diffusion. So diffusion is basically because of the difference in the gradient, difference in the concentration. Very basic physics. If you have if you the whole concept of, sorry, yeah, so very basic physics. What does that states? That there will be always flow of things from higher concentration to lower concentration, and till the equilibrium is achieved. So here you are having higher concentration of your one types of charge carriers, and in the other part you are having another type of charge carrier. So automatically, because of laws of physics, there will be a diffusion that will start happening. So one part is the diffusion part. Okay, the other part would be, so once you have these diffusion at the interface, then because of this diffusion there will be a recombination, and then this recombination will lead to a generation of electric field which will oppose this diffusion. Okay, and then when you're talking about external biasing across the PN junction, I don't have a blackboard, otherwise it would have been much more convenient for me to explain further. Moment you are talking about this external voltage along with this internal built-in potential which oppose the diffusion part between two different types of semiconductor material based on their doping concentration, this will lead to the other part, which is the drift current. So there will be a diffusion current and the drift current. So that is happening. And when we are talking about MOSFET, that is just an extension of this PN junction. So this drift diffusion will happen all over the place. And there will be one due to the diffusion gradient, concentration gradient between different types of semiconductor materials, and also between different types of material like metal semiconductor, like oxide or dielectric semiconductor or metal dielectric. So those are different types of interfaces that are getting formed in your transistor technology. Am I? Is that clear? Hello?
Yes, sir. Yes, sir.
So this will help you to answer things like gate voltage of a device. When do you turn it on and when do you turn it off? Like in a simple PN junction, you have these external biases which would lead to either depletion of your depletion width depending upon the external bias. If the external bias is what you if the external bias is a positive bias, then this depletion width will squeeze down, it will go down. And if the depletion width if the external bias is a negative bias, then this depletion width will increase. So this depletion width basically is related to doping concentration, to drift and diffusion, and the built-in potential. Okay, so this width of your depletion can be changed or manipulated or can be guided by applying external bias. So there we are just talking about P and N. So that is one type of junction, one type of semiconductor, another type having a junction. So that forms one type of interface. The other is the metal semiconductor. So moment we are talking about P junction and N junction, they are connected to metal. Otherwise, how would the biasing happen? So there is a metal semiconductor both in the P region and N region of a diode configuration. Hello? At least let me know
Yes,
whether
sir.
it's possible or you know. Okay, are you
Yes,
there?
sir. Yes,
Yeah.
sir.
So this, when you expand to the MOSFET configuration, you will see that there is an inversion layer that happens because of the difference in the PSA N plus source and N plus drain and P plus body. And when you apply, and that is why there is a kind of a depletion region all across the interface between your source and body, drain and body, as well as the oxide layer and the body. So here you are having gate, which is probably a metal. Then you have oxide, which is a kind of an insulator. Oxide basically means an insulator. So it's basically silicon dioxide. It's not oxide per se, it is silicon dioxide. Silicon dioxide. So it is acting as an insulator. What is the difference between metal insulator and semiconductor? Anybody?
So their conductivity, like electrons conductivity.
Okay, good. And any other points? Yeah, that's fine. Any other points? Also in terms of its, yes, class. सुनाई नहीं पड़ा क्या? I'm not able to understand what you said.
Sir,
Sounding,
band gap.
yeah, band gap. Correct. So so what type of band gap is there for all the three different
Sir,
cases?
metals have an overlap of the conduction and insulation band. Non-metals have a really big band gap, and semiconductors have a zero point 0.2 or 0.3 volt band gap.
0.2, 0.3? Which one are you talking about? 0.7 around of the order of 0.7 for germanium, 1 point
Yes, sir.
around
Sorry,
of the
sorry, sorry.
order of
Right, right, right.
1.1 electron volt. Please say in units. How about insulator? Yeah, few electron volts. Okay. Yeah. So basically, by applying this external bias, then you have what you call as the inversion layer that forms, not the depletion layer. And through this inversion layer, there is the movement of the charge carrier. So if this is p body, so it cannot. If this is electrons. P body means holes are majority carriers in this region, and this is the depletion region. So from source to drain, there cannot be any kind of conduction if it is depleted of charges. It can only happen when there is a reverse inversion of charges. What does by the English word itself, what does that mean? That in the p type, if at the interface, at the oxide semiconductor interface, MOS is oxide basically means insulator semiconductor interface. If at very small dimensions of few hundreds of nanometer, you are able to inverse means if it's a p type of body, what would be the majority charge carrier? What would be the majority charge carrier if you have p type of body in this region?
Holes.
Holes. So if you are able to somehow make this region switch from holes to very close to them to electrons, then only there will be flow of charges from source to drain, and that is governed by, or that can be regulated by putting various biases, external biases like the gate bias, the drain bias, and so on. So once that bias at the gate is achieved, then the device is basically turned on, and in technical terms what you call that voltage is the threshold voltage. So threshold voltage is the voltage when your transistor becomes, there is an inversion of charge carriers that happens at the insulator semiconductor interface, and there is a flow of charges from source to drain by applying appropriate gate voltage. And that voltage that you apply to the gate is also defined as the threshold voltage. So since this is related to the on and off state of the device due to the resistance between the source and the drain of the device. So you need to understand these different types of interfaces. And that would also relate to the speed of the device, because we talked about two types of conduction, the drift and the diffusion. So the drift is basically happening because the bias that you apply, and that is related to the speed of motion of your charge carriers inside the semiconductor. So what is, so in semiconductors, how is drift velocity related to the motion of charge carriers in semiconductor? Class, hello?
Sir, we can use the same I equal to NEA VD relation.
No, what is that? You're talking about Poisson equation?
Sir, I don't think it's called the Poisson equation. It's
What
one of the equations we were taught
if
when
you apply a simple bias in a semiconductor? The motion of the charge carrier in that semiconductor is defined by your what? Drift velocity, which is dependent on the,
Field we apply around it.
yeah,
The
mu e,
voltage. Yes, sir.
that is dependent on the mobility and the applied field. Correct. I think you must have done these things before.
Yes, sir.
So this mu e is basically dependent on the applied voltage at drain and the overall MOSFET transistor. That is why it is called field effect transistor. So the field that is generated due to the applied voltage at the drain.
Sir,
Yeah.
So we have a class. We have other class right now.
3 or 310?
So it's 3-5, I guess. I'm not sure.
Okay. So please revise your device this thing and we will accelerate from here. Is it 310 or?
Sir, it's 3-5.
Okay. Thank you.
Thank you, sir.